Hello students, today we will see the concept of universal hashing and the Bloom filter in this video. Now we have seen hash function, which is a very useful function for the purpose of mapping of a large elements, a high range of elements into a small domains or the small range of values, and which is important for the purpose of various applications like we have to put a large data into small area, small memory requirements and so on. Okay, now we have a family of functions. We have multiple functions under this hash functions, where we use randomness to sample the hash function. We create a hash function based on some random function, and we select a random function from this hash function. So we call it to be a family of functions, which is a universal hash function. So here we see h is equal to a small h, which maps the element from this universal element or the universal set of elements to real numbers, which is a family of functions. We have a variety of applications of these hash functions, data structures, and the streaming algorithms. We are going to see a streaming algorithm, which is a Bloom filter, in this video. Now, universal hashing, as I said, we have the fixed hashing, which is vulnerable to bad worst case behavior. It means that when we are putting the high range of values into a small range, it is quite possible that we have a collision of the same bucket or the same value multiple times for multiple input values. So this is a worst case behavior that we want to avoid, that we don't want in case of this universal hashing. So the universal hashing, it is used for the purpose of improvement of the behavior by choosing a hash function randomly independent of the keys. Okay, so we have some randomness in choosing of this hash function and it's independent of the key values, and it produces a good performance on average independent key choice. So we get a good performance in every case, on the average case as well as, and in the worst case behavior too. So we don't have the collisions for the same key values multiple times, and we allow the proper spread of the values for these all input values from a large domain to the small domain of key values. Now, what are the various desired properties of a good hash function which should be behaved considered as a member of this family of function, which is a universal hash function? So the very first we say is the keys are nicely spread out. So as I already said, the keys should have nicely spread. It means we should have a proper choice for every of the key values. You should have the equal probability to match with every key values for the given input values. Then second, we say that m is equal to O of n. So we say that it should be a constant this time complexity we should have for the n number of independent large number of values. We should have the m number of key values. So we say that generally we should have this complexity to be m, which is O of n, and which is a constant complexity. Then next we say that the function h is fast to compute. The h function, the hash function, should not be very complicated. It should be a very easy function to map, like our normally mod functions are used for the purpose of the hash functions or so. Okay. So these are the three important desired properties of any good hash function. Then considering this universal hash function, considering these desired properties of hash function, we have a concept which is called as universal hashing. Okay. So what is this universal hashing? A randomized algorithm H for constructing the hash functions H, okay, which is a mapping from the universal function U to the 1 to m number of key values. So we are mapping a large domain values U to the m number of key values, which is universal if for all x not equal to y, which are the input values from this universal set, we have probability that h of x is equal to h of y, it is less than or equal to 1 upon n. So it means that we should have the equal chances for all these m key values to be as output for the various inputs which are x and y. Okay, and when there are two hash values to be equal, the probability should be less than or equal to 1 upon m, so that we have a nicely spread up the values for the key values, and equal chances should be given for every key value to appear as output for the input value. Okay, so a set H of hash functions in universal hash function family, if the procedure choose H from this capital H at random is universal. So it means that we want to choose a H function, a small H function from this capital H, a family of hash functions randomly, and it should be a universal process. It means that it's a random process, and we should have equal chances and all the desired properties to be followed for this hash function. Okay. Now considering all these universal hashing, then hash function, properties, and these probability values, we have an application which is called as a Bloom filter, and it has some algorithm how we can implement the Bloom filter. Okay, so for this purpose, we see an example like we have a set S of 1 billion allowed email addresses. Okay, and typically the email address is of 20 bytes or more. That is what the normal size of the email address. And we want to store this email address in the main memory. So we cannot store this email address in the main memory, because if we see 1 billion into these 20 bytes, that comes out with 20 GB, and our main memory is not of that much of size. So we should have implemented this concept of storing these email addresses in some other way, that is a Bloom filters. So in this technique of the Bloom filtering, the main memory is used as a bit array. So instead of using each byte for a purpose of the storing, or the 20 bytes for storing as it is, what we do is we have just a single bit to be considered presence or absence of the email address as the data set. Okay. So here the room for 8 billion bits is made over here, isn't it? So we have this 8 bits and we have this 1 billion addresses. So we consider, or we require 8 into 10 raised to 9 number of bits. So for this purpose, what we do is we are devising a hash function h from email address to 8 billion buckets. Okay, so don't consider this to be the 10 million values, but we consider the 10 billion into 8, because every bit is standing as a one value for the one email address. Okay, so let us see the details of this Bloom filter in the next slides. So here in the Bloom filter, the hash function is used for each member of S to a bit and set that bit to 1. If email address is present, we make the bit to be 1. And if it is not present, we set to be 0. Okay. Now approximately 1/8 of the bits will be 1, because we consider that one bit is used for one email address. There are 8 into 10 raised to 9 number of bytes available with us. Okay, bits available with us. So we just want 1/8 of the bits to be 1. And the exact fraction of the bits set to 1 will be slightly less than 1/8, because multiple times multiple email addresses may hash to the same bit value. Okay, and we allow this to be happen in this case. So there is a collision, but we handle it some other ways. So what is the strategy? We will see that when a stream element arrives, hash its email address. So we have a stream element, we have the email address, we find some number value out of that, and we hash that number value to get some value which is mapped to a bit number in the memory. If the bit to which that email address hashes is 1, then let the email through. Okay, so we get the one value, we get that one value is presence of the email, we allow that email through, means we consider that email for our processing purpose. Okay, and if the email address hashes to be 0, we are certain that the address is not in the S, so we can drop this stream element. So we have a set of S, we have the set of S as a email addresses. We have already hashed these email addresses. If it is present, we set is 1. If it is not present, we set this to be 0. Okay, as a bit value. And we check the existence of these email addresses in the stream as it comes to us. So there are 3 elements which are required for this Bloom filter implementation. An array of n bits, initially all zeros. Okay, collection of hash functions. Now see, we are not using a single hash function there, but we are using a family of hash functions like h1 to hk. Okay, k number of hash functions are required over here. The set of s, which is the m key values. Okay, so we have the key values, we have the n bits. We are putting these key values to the bits which are actually to be stored as a memory content. So the purpose of the Bloom filter is to allow through all the stream elements whose keys are in S, while rejecting the most of the stream elements whose keys are not in S. Okay, so we want to get this as a whether we should throw the email or not, that we are going to check. So the algorithm for this is to initialize the bit array with all the 0. Okay, then take each key value in S and hash it using each key of K hash function. So take a value from this S string, hash it with a K function, each of the hash K function h1, h2 up to hk, set to 1 each bit, that is hik, for some hash function hi and some key value k in S. Okay, so set it to 1 if it is giving some value as per the sequence number in the n bits, to test a key k that arise in the stream. So this is the initial setup that we did in the first 3 steps. When the we want to test for a particular key which arise in the stream, check that all this h1k, h2k, all these hash functions are once in the bit array. Okay, If all are ones, then let the stream element through. Okay. So if all are ones, then only we allow that email address and we consider that as valid email address. If one or more of these bits are 0, then K would not be in the S, so reject the stream element, reject that email address. So we are going to check the validity of the email address considering this Bloom filter algorithm. Let us see the example to understand this Bloom filter in detail. So we insert and query on a Bloom filter of size m is equal to 10 and number of hash function k is equal to 3. Okay. So we have this 10-bit long array, which is 10 values are there, 0 to 9 values, and we have 3 hash functions. Okay. So h of x, you know the result of the 3 hash functions, which we write the set of 3 values h1 of x, h2 of x, h3 of x. So h of x is a family of hash functions. It's a universal hash function, and h1, h2, h3 are the elements of this hash function that we are going to use for our Bloom filter implementation. Okay. So initial setup is like this: 0 to 9, all bits are set to 0. Now next, we have a first x0 element. We find out this h of x0, the capital H. We get the individual hash function values to be 149. So these are the key values we obtain after the first hash function implementation. Now we set these key values to be 1 in the bit array of the memory. So we set this 1 to be equal to 1, then 4 to be equal to 1, and 9 to be equal to 1 as per this 149, which are the key values of the first hash function, or the first element rather. Then for the second element x1, we again find this h of x1 and we get the values to be 4, 5, 8. Okay. Now the 4 is already 1, so we are not going to change anything. Then 5 is made 1, 8 is also made 1. So we see that the 1, 4, 5, 8, 9, these all bit values will be 1 after these 2 elements which are inserted as a part of memory storage. Now we see this is the overall setup now. H of x0 is 149, H of x1 is 4, 5, 8. Okay. Now the query arises where we get the element y0. We want to check this y0 and we find this h of y0. We get for this y0 as 0, 4, 8. Okay. So we check 0th, 4th and 8th element, but 0th element is not 1, 4th and 8 is 1, but we want all these bits to be 1 to consider this to be valid email address. So we say the output is no for this particular y0. Now there is second email address which arises, which is a y1, which we find the all 3 hash functions and we get the key values as 1, 5, 8. Okay. Now we check that it's a 1, 5, 8, all are ones. So we say that it's a correct email address and we say the output is yes, because all 3 values at the bit values 1, 5, 8 are ones. Okay. Now understand this point. We have the first input as a 149, second giving the hash value to be 4, 5, 8. But considering the querying part, considering the checking part, we have 1, 5, 8 and we are allowing this email address which gives these hash values to be correct email address and we say it is yes, means it is a valid email address. So we say that when we are having the correct email address as 149, 458, we allow it yes, that's very sure. But if some combination of the email addresses arises which gives a combination of the hash values, then in that case we say that it is also giving the yes as an output. So it means that it's a false positive. Okay, false is said to be positive, false is said to be a correct email address. So that is not a correct, but still we are saying it's a false positive. So understand the point. When we have the valid email address, we allow it to pass through, we allow it to be considered as a valid email address. But when it is not valid email address, there is a it's totally valid, not an email address, then we are not allowing it. Okay, but if it is not rejecting the correct email addresses. Okay, so the point is it is not rejecting the correct email addresses, but may allow the wrong email addresses to pass through. So there is a small false positive probability value associated with this particular algorithm. Okay, so I think everyone must have clear this algorithm, which is a Bloom filter algorithm. We have the various family of hash functions. We have the input values like x0, x1. We are finding the output for every of the hash function. These are the key values which we obtain. We put these key values as in the bit array, which is like a n bit array here, 0 to 9. Okay, we make all these ones. This is the registration part. This is the first step, initial step, we can say. And after that, when we query it, we check whether all ones are there at the locations, which are the key values which we obtain after this hashing. Okay, if all are ones, we say that it's a valid email address. If any of the one is not available there, if some is 0, like in this case 048, we have the 0 at 0th bit, then we say it's a no. Okay, and in this case we have a small false positive probability that we allow some non-valid email address to be a valid email address. Okay, but we are not rejecting the valid email addresses. Okay, so considering all this, we say that the Bloom filter is very important for the implementation. Like we have seen the example of email addresses filtering and all, and having a very small false positive probability, like the probability is 1 minus 1 upon n raised to k into m. Okay, so we have m number of key values, we have the k number of hash functions, so it's a very small probability value to with that, and that's what we can implement this Bloom filter using the universal hash function concept. Thank you.